Welcome to part 3 of our probability video series. You can follow along using your probability guided notes starting on page 5. First, we're going to talk about non-mutually exclusive events. If we have events A and B, then the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. That's called our addition rule. It can also be read as the probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. Whenever we see a probability problem that has OR, that's our cue to use this addition rule. I'm going to use OR and throughout this section rather than union and intersect. Here's an example. Let E be the event of spinning an even number on the wheel we see here to the right. The even numbers are 2, 14, and 18. We're going to let T be the event of spinning a multiple of 7. The multiples of 7 on the wheel are 7, 14, and 21. So when we find the probability of E or T, that's the equivalent of finding the probability of E plus the probability of T minus the probability of E and T. So let's see here. The probability of spinning an even number would be 2, 4, 18. So 3 numbers out of the 8 on the wheel. So the probability of spinning an even would be 3 out of 8. The event T, we have to find probability of event T, getting a multiple of 7. There were 3 multiples of 7 out of the 8 numbers on the wheel. We now need to subtract the probability of spinning a number that is both even and a multiple of 7. Well, looking at E and T, there is one number that is both even and a multiple of 7, the number 14. So we're going to subtract 1/8, and we'll get 3/8 plus 3/8 is 6/8, minus 1/8 gives us 5/8. The probability of spinning a number that is even or a multiple of 7 is 5/8. Some of you may ask, why did I have to subtract this 1/8? Well, the number 14 is accounted for in the 3/8 for the probability of an even. The number 14 is accounted for again in the 3/8 representing the probability of a multiple of 7. So because it's accounted for in both places, it's counting more than we actually want it to. So by taking away 1/8, we're making sure that that number 14 is only accounted for in one of the probabilities. Another way we could have come up with this answer, the probability of spinning an even or a multiple of 7, is simply looking at the wheel. And we could check off any numbers as we go around the wheel that are even or a multiple of 7. Doing it this way, it would ensure that we're not counting anything more than once. Unfortunately, this method isn't easy for all probabilities. That's why the formula can be helpful. In our next example, we have a golf bag that has 2 red tees, 4 blue tees, and 5 white tees. We want to find the probability of event R that a tee drawn at random is red. Well, I can see that there are 2 red tees out of 11 total. So that probability is 2/11. Next, we have what is the probability of the event not R, so that the tee is not red. Well, that's R complement. So we can say 1 minus 2/11, or 9 out of 11. Another way to find this is if it's not red, then that means it would be blue or white. So we could have simply said there are 4 blue tees plus 5 white tees out of 11 tees total, and we would have gotten 9/11. Either method's okay to use. For part C, what is the probability of the event that a tee drawn at random is red or blue? Well, there are 2 red T's out of 11 T's, plus 4 blue T's out of 11 T's. And there are 0 T's that are both red and blue at the same time, so I'll subtract 0 out of 11, and I'll get 6 11s for my total. For part D, we have what is the probability that a T drawn at random is both red and blue. So the probability of red and blue. Well, I kind of just answered that right here. There are 0 T's that are both red and blue at the same time. A couple more notes before we move on regarding the significant results and probabilities. First, we have the rare event rule for inferential statistics. If under a given assumption, the probability of a particular observed event is very small, and the observed event occurs significantly less or significantly greater than we typically expect with that assumption, we can say that that assumption is probably not correct. So how do we use that to determine significantly high or significantly low? This is a concept that we explored in the last chapter using standard deviations. Now we're going to use percentages or decimals. So, for significantly high number of successes, if X successes among N trials is significantly high number of successes. If the probability of X or more successes is unlikely, with a probability of 0.05 or less. So in short, we have the probability of X or more successes is less than or equal to 0.05. So if you're coming up with a probability of less than or equal to 0.05, that's kind of your magic number. There's a note here that this isn't absolutely rigid, but unless otherwise stated, we're going to use 0.05 as that magic number for significance. For a significantly low number of successes, we can say that we have a significantly low number of successes if the probability of X or fewer is unlikely with a probability of 0.05 or less. In symbols, we have the probability of X or fewer is less than or equal to 0.05. So once again, if we're getting a probability of X or fewer is less than 0.05, that's our magic number, we can say we have something significantly low. If we're getting a probability of X or more being less than 0.05, we can say that our probability is significantly high. We've learned a lot. Let's do some practice problems before we move on. If you feel like you're all set, you can do them on your own and check with the key. Otherwise, hang in here with me. Number 1, a random sample of 317 new Bright Smile electric toothbrushes showed that 19 were defective. A, how would we estimate the probability that new Smile Bright electric toothbrush is defective? What is your estimate? Well, we'd estimate that by using the data that we have. So we have 19 are defective out of 317. So that would be our estimate for defective toothbrush. For part B, what's your estimate that the probability Smile Bright toothbrush is not defective? Well, we could have a sample space of defective or not defective. So we could say 1 minus 19 over 317. And that gives us 298 out of 317. And it would be okay to represent these as decimals to 3 decimal places. I'm leaving them in fractional form so you can see the process. Part C, what is the sample space of this problem? Do the probabilities assigned to the sample space add up to 1? As stated before, the sample space is defective or not defective. And when we add up our probabilities from A and B, we do get 1. Number 2, if you roll a single fair die and count the number of dots on top, what's the probability of getting a number less than 3 on a single roll? Well, the numbers we could get are 1, 2, 3, 4, 5, and 6. We're looking for numbers less than 3. That's a 1 or a 2. So you have 2 out of 6 probability, or 1/3. Let's look at page 7, number 1. If the probability of an event is 0.27, then the probability that that event won't happen, if it's event A, we'll say not A, is going to be 1 minus 0.27, which gives us C, 0.73. Number 2, if event A is certain to occur, what's the probability of A? Well, anything that's certain to occur has a probability of 1. And number 3, a coin is tossed 1,000 times. What's the probability that the 785th toss is heads? Well, each toss is an independent event, so it doesn't matter how many times we tossed it. For a fair coin, the probability of a head is 1/2. C. Question 4, we're going to use our standard deck of playing cards. Remember, you have some notes on the standard deck of playing cards in a previous section here, and you can use it as reference. So we want to find the probability of getting a jack or a king when you draw one card from a deck. That's going to be equivalent to the probability of getting a jack plus the probability of a king minus the probability that you draw a card that's both a jack and a king. There are 4 jacks in the deck out of 52 cards. There are 4 kings in the deck out of 52 cards. There are 0 cards that are both a king and a jack. So for a probability, we'll get 8 out of 52. If I divide both parts by 2, I'll get 4 out of 26, or 2 out of 13 for my final answer. And you can leave that as a reduced fraction. For part B, we're finding the probability of a king or a diamond. Well, that's the probability of a king plus the probability of a diamond minus the probability of a king and a diamond. Let's see. Once again, there are 4 out of 52 cards that are kings. There are 13 out of the 52 cards, or 1/4 of the deck, which are diamonds. And there is the king of diamonds, so there is 1 card that's both a king and a diamond. So let's add that up. We have 4 plus 13 is 17, minus 1 is 16 out of 52. If I divide both parts by 2, I'll get 8 out of 26, or 4 out of 13 for my final probability. Last example for the deck of cards is the probability of a 5 or a red card. Well, that's the probability of getting a 5 plus the probability of getting a red card minus the probability of a card that is both a 5 and red. Well, there are 4 5s out of 52 cards. There are 26 out of 52, or half the deck is red. And let's see, there's the 5 of hearts and the 5 of diamonds, so there are 2 red cards that are 5s. So we'll have 26 and 4 is 30. 30 minus 2 is 28 out of 52. That's 14 out of 26, or 7 out of 13 for our final answer. For our last example, we have Professor Jackson's in charge of a program to prepare people in a high school equivalency exam. Records show that 80% of students need work in math, 70% need work in English, and 55% need work in both areas. You can see I've written that information symbolically right here. So we need to find out, are the events math and English needs mutually exclusive? Well, they're mutually exclusive if the probability of math and English equals 0. And that's not true because it's equal to 0.55. So, no, they're not mutually exclusive. Part B, we want to use our formula to find the probability that someone needs help in math or English. Well, that's the probability of needing help in math plus the probability of needing help in English minus the probability of needing help in math and English. Fill in the formula. 0.8 plus 0.7 minus 0.55, which is equal to 0.95. So the probability of needing help in math or English is 0.95.